Introduction. Yeah, like you said, this is talk will be presented in a different manner, and also the contents will be somewhat different from most of the talks that we have heard today. So usually, the participants here interested in waves have taken either applied mathematician approach of using some sort of asymptotic expansion to study this kind of waves, or computations for to investigate large amplitude steady matter waves. So I will. So this talk will be mathematical analysis of these equations. So my ultimate goal is to show you some results about the existence of waves of large amplitude. I will discuss three different types of surface wave problems. So classical gravity waves and capillary-gravity waves, and more recent some waves that are of most interest to participants in this workshop. So waves under an elastic sheet, so which could be regarded as a model of waves under ice. So even if one is most interested in the last subject, so as being related to ice, I think that the results available for this type of waves are best understood if we regard them in comparison to results for these other types of waves. Of course, there is an absolutely huge literature on all of these problems, so I will only give a selection of results, and in general will not give references. But this does not mean that I claim any originality, except maybe in a little bit in the final part. So there is like a small new idea about hydroelastic waves. Okay, so one of the since I will concentrate mostly on irrotational waves in two-dimensional irrotational flows. The one essential ingredient of the approach is the use of complex analysis and conformal mapping. So I will say something about that and about the Hilbert transform, which can be used in the description of in a reformulation of these free boundary problems. And then the existence results will be obtained as a consequence of abstract results in global and bifurcation theory, and so I will spend most of the talk discussing these results, a few of the main results available, and this would require some preliminary background material on differential calculus in Banach spaces and compactness. Okay, so the aim of the talk is to show that how some very general and abstract results can be used to give to prove the existence of waves of large amplitude. So let me start with the fluid equations in the simplest setting, that of two-dimensional waves under gravity. So I will go slowly. If there is anything that is not very clear, please do not hesitate to interrupt me and ask questions. So this will be a two-dimensional problem formulated in the xy plane. Describing, well, for fluids with a free surface, fluids and of infinite depth. So we have a fluid region which extends to minus infinity in the vertical direction, and which is bounded above by a free surface, which in this introduction is assumed to be the graph of a function, although it doesn't have to be. And above the fluid we have air. And then, because the water is considered implicit incompressible fluid, so the dynamics is described by the Euler equation for a two-dimensional velocity field UV and pressure. So subscripts denote partial derivatives. The only external force acting on the fluid is gravity. We have the incompressibility condition at infinite depth, as y goes to infinity, the fluid is at rest. And on the free surface, so we have this kinematic boundary condition that the same particles always form the free surface, and in the gravity wave problem, the pressure on the surface is equal to the constant atmospheric pressure. In the other two models, this will be the only different thing. I will tell you later how this condition changes. Okay, so I will be interested only in traveling waves, for which the fluid is in a motion which is stationary in a moving frame at velocity c. So we assume that the surface is translating at the velocity c, and the velocity field and the pressure. So the dependence of x and t is only through this combination x minus ct, and the function depends on the y variable as well. And so all the functions depend on two variables, and we work in the moving frame, and we will just replace this x minus ct by variable x. Okay, then in the moving frame, because of the incompressibility condition, as it is well known, the flow can be described by a string function psi, whose skew gradient gives the velocity field. And if we eliminate the pressure from the two equations by differentiating it with respect to x, we get that delta psi and psi have a parallel gradient, so it is this relation, and then the vorticity, which is okay, so the sign can be taken to be different. This will not be important, but delta psi is constant on the level set of psi. So under quite general situation, we can assume that the vorticity is a function of the string function, but this could be any function. And then if we know the string function psi, then the pressure can be recovered by Bernoulli theorem. We can check directly that this expression, which involves the primitive of the vorticity function little gamma, so this is constant in the fluid, and because p is constant at the surface, it would follow that this expression here is constant at the surface, and then this is also zero. So overall, so the entire problem will be formulated in terms of the string function only. And I should say that for most of the talk, the vorticity will be taken to be zero. So the string function satisfies in the fluid domain a semi-linear equation in general, or is a harmonic function in the irrotational case. It takes a constant value on the free surface, which we choose to be zero. Because of the pressure being constant, we get this form of the Bernoulli condition for the gravity wave problem involving a constant, and at infinite depth we have this relation for the gradient of psi. So the fluid domain is bounded above by an unknown free surface, which is a curve S, and I will consider throughout what follows only periodic functions. Although, as you know, so this problem, I mean, one can also examine solitary waves, so this instead of periodic one, and one can look at waves of finite depth. So again, yeah, G is gravitational constant, C is the wave velocity we have. So what if we and now as I said, in the other two problems, the capillary-gravity wave and the hydroelastic wave, so all the equations remain unchanged, except for the Bernoulli condition, which now takes two different forms. So here sigma is a, so this is a capillary gravity wave problem. Sigma is a positive coefficient of surface tension, and the k is the curvature of S. So this comes from the fact that the difference in pressure the difference between the pressure in the fluid and the atmospheric pressure is a constant, is a multiple of the curvature of the surface. While in the hydroelastic wave, so now above the water we don't have air, but we have a thin elastic membrane, and in that case the pressure in the fluid acts as a forcing term in the equations on the membrane, and then the membrane acts somehow also on the fluid. But okay, so the conclusion is that we have an additional term in the equation which involves again the curvature, but power cube, and also the second derivative of the curvature with respect to arc length and an additional coefficient. So this model has been used by quite a few people recently who may be able to tell more where it comes from and so on. So I am interested in the analysis. So we have these three types of problems that will be considered in what follows. Okay? Questions? Okay. So yeah, some comments about possible extensions and other comments. So there is a finite depth version in which instead of the condition of the infinite depth we have a flat horizontal bottom and a constant differential boundary condition. In the infinite depth we can remove this Bernoulli constant and replace it by c squared over 2, because we have the freedom to translate or to choose the axis to translate the axis. So we can take these values. I will discuss in what follows almost exclusively the irrotational waves case, in which there is no vorticity, and in this situation the approach that has been used relies heavily on complex analysis. If we have vorticity, then none of this is available. One has to use completely different arguments, except in the case of constant vorticity, which can also be treated by means of complex analysis. Yeah.
I have a question. So gamma is a vorticity function, right?
Yes.
So just wondering, so what kind of vorticity function is physical?
Okay, I think the constant is the most natural case, let's say. But the idea is that the constant vorticity describes waves propagating on a pre-existing current. So for trivial flows, we have fluid at different velocities at different heights, and so you assume that there is such a flow, and this somehow tells you how the vorticity varies with height, and then you see this determines gamma somehow. This is a bit tricky, actually. It has not been properly addressed, I would say. But
so you mean you have a shear current?
Yeah. This waves and vorticity are
so the
waves and shear current.
So the wave can propagate with different speed.
Yeah, then the speed of the wave is not well defined, and I mean it's not.
I'm very confused sometimes when I do this. Oh, it's fine.
Yeah, well, so I think constant vorticity should be okay. So it means that you have
you have a linear speed.
Yeah, you have a linear profile, let's say, but which you can also take it maybe translating at different speeds. So you increase this arrows by a certain amount, and then so So this determines a constant, so the slope of the, and then you use just the that constant in the equation, delta psi equals that constant.
But how is that, I mean, you're drawing this linear shear, I mean, how does that fit with no, presumably you've got no flow deep down?
Yeah, okay, so in
infinite depth,
this makes sense for finite depth only, indeed. So for infinite depth, the vorticity has to go to 0 at infinite depth. So constant vorticity on infinite depth is not a physical problem.
This is it with the basic boundary.
Yes.
Although it has been used by serious people, I mean,
to generate the linear shear.
Numerically have been done
This has
with the constant vorticity and infinite.
Yeah.
Some more.
Yeah.
I've got
I
a
know.
question.
please.
So are these equations, I mean, in our group, well, in our department, there are loads of people that do fluid-filled tubes. So does this have, these hydroelastic problems, do they have links to flows in collapsible tubes and things like that?
This I don't know. Maybe somebody else can answer. So
This is sort of like the mirror image of this problem underneath. So you've got two flexible elastic walls
yes.
and then some fluid.
That's
Hmm.
right. That's
Yeah.
right.
But I think you have some three-dimensional effect on that one as well. So the curvature is more complicated.
If you have tubes.
Yeah.
There is some monotonicity conditions on gamma.
well, I will discuss almost exclusively irrotational flow. So gamma was just to say that. So this will involve a heavy use of complex analysis, and I just wanted to say that if we have vorticity, then that doesn't work, and one has to do something different. So I want to get to Babenko's formulation and those kind of things. So it will not be about gamma here. Yes. Yeah, and okay, so the elasticity of the membrane can be also modeled in different ways. I think this is one of the simplest. Yeah, I don't know. So I'm not good at this modeling part. So maybe other people can make more comments. But okay. So what is known about and what kind of results are we interested for this kind of problem? So for the gravity wave problem, so let me mention what Stokes believed and conjectured about this wave. So he said that there is a family of trivial waves, okay, parameterized by the fluid velocity, like I said, and depending on the wave period, so at a certain value of the velocity, there will be small amplitude waves bifurcating from trivial flows. So this you can, I mean, and he studied them a little bit with some asymptotic expansion. But then he said that this family can be continued into a family. There exists a family of waves parameterized by amplitude, and there is a highest wave with a stagnation point at the crest and the with a corner of 120 degrees on the crest. And so assuming existence of this wave, he gave some formal arguments about the corner, but this he gave no indication why it should be true, and there is a family of wave going from flat to this. So all of this has been rigorously proved like 100 years later in the 60s, 70s. This is specific to gravity waves, so we are not going to have anything like this in the other two fluid models. But I am interested in proving the existence of a family of waves like this, and this is. This is a problem with parameters, so it is we can call it bifurcation problem. I'll give a definition of bifurcation, what bifurcation problem is. Okay, but first of all, one of the, so if we want to study waves like this without any restriction on the wave amplitude or on the geometry, it is very difficult to do it in the physical plane where these are free boundary problems, the domain is unknown. So the idea is to reformulate them over a fixed domain. And in the irrotational case, so this approach goes back to Stokes again to observe that irrotational waves we also have a velocity potential that is harmonic conjugate of the string function, and together phi and psi determine a conformal mapping between the fluid domains and a house plane. And this is the, and then instead of seeking, well, what here we can call the coordinates phi and psi. So instead of seeking phi or psi in this unknown domain, we look rather for the inverse conformal mapping, and which involves solving a problem in a half plane. And because all of the functions are harmonic, this will be, well, Stokes did not do this, but this is what we're going to do. We're going to reduce the problem to an equation on the real axis involving functions of one variable and the Hilbert transform. But okay, so I'm not going to use directly this. Just I will consider a conformal mapping to any region that could possibly be occupied by the wave. So momentarily I will ignore the fluid equation and assume just that we have a periodic domain with unknown boundary, which is periodic but could have arbitrary complicated shape. So there is no need for any assumption about the geometry or the amplitude. And by the Riemann mapping theorem, so given this region, no matter what it is, there will exist a conformal mapping from a half plane to the region below this curve. And so, so the half plane, so I'll denote this function by u plus iv, so okay, no connection to the velocity. So the conformal mapping is u plus iv. These are real valued functions, and they have some periodicity. So the periodicity of this region leads to some periodicity of this function here. And while so this requires a bit of analysis, so we normalize the period here to be 2 pi. And then while the function v is 2 pi periodic in the horizontal direction, so 2 points at distance 2 pi will be mapped to points at the same height, but u, yeah, so points are like this, but the u coordinate is not the same, but is different by the period of the wave, which I took, yeah, so the period was initially L, and I take it to pi over k, so that would correspond to the wave number. So this conformal mapping exists, and it has this kind of periodicity condition. And moreover, so for this to be satisfied, this function must involve a multiple of the identity with a coefficient of 1 over k, plus 2 functions which are bounded and periodic. So, so this I cannot explain in more detail, but it is true. It is well understood. So there is this. Yeah, so somehow, and the real axis will be mapped into the curve S, and 2 points at horizontal distance 2 pi here will be mapped into 2 points again at the distance equal to the wave period. And the point somehow where I want to get is that so we want to determine the domain. This means that we would like to determine this conformal mapping. This mapping is determined by its imaginary part, which we may consider either V or V tilde. And this in turn is uniquely determined by its restriction to the real axis, which I will call little w, and namely, sorry, little v. And how is that? So if we know the values on the axis, little v, then capital V tilde is determined as the unique solution of the Laplace equation in the half plane with boundary values little v on the top and with the boundedness conditions at infinity, which actually implies that, that this goes to 0 at infinity. And then U is the harmonic conjugate of that. And as you have, I mean, if you look at this, you are probably familiar. So the and the boundary values of capital V and capital U on the real axis are related by the Hilbert transfer. So so if we have, okay, this we don't need. If we have a periodic function, we solve the Laplace equation. We take a harmonic conjugate, and then we take the restriction of that to the real axis, and that by definition will be the Hilbert transform of the function that we have started with. So this is in the half plane, but this analysis is most often done in the unit disk. So because periodic functions in a half plane are essentially the same as functions in the unit disk, with the origin corresponding to minus infinity, where our functions have regular behavior. So somehow the idea is that if you have an analytic function in the disk, then the real and imaginary part on the circle are related by this Hilbert transform. And if we take the function z to the power n, so which is analytic, and if we restrict it to the unit circle, then we have cos nt plus sine of nt. And the Hilbert transform maps this into this. So Hilbert transform of cosine is sine, and also if I take this out to the power like this, the Hilbert transform of sine is minus cosine, and this is a linear operator defined by the. Okay, so if you have seen this before, it will be very familiar. Otherwise, maybe it's a bit of thinking to fully understand it. But okay, so the Hilbert transform, so conjugation operator or Hilbert transform, so maps acts on the trigonometric system in this way, and it also can be represented as a convolution with cotangent over 2. Okay, and so this is true both in the disk and in the half. And therefore, so as I said, the conformal mapping from the half plane to such a domain, periodic domain in the plane, it will be determined by the restriction of the real axis of its imaginary part. And if I introduce this scaling factor 1 over k, so the boundary of this region will be parameterized by the conformal mapping restricted to the real axis, whose imaginary part is okay, maybe it was the other way around. Yeah, probably. So there is some error here. So you maybe just ignore this factor 1 over k for simplicity. So So what I want to get is that this curve admits a parametrization which has some imaginary part here, and then the real part is just the Hilbert transform of that, and there is also a multiple of x because of this translation property that I discussed earlier. So this is true for any periodic region, so the boundary can be parameterized in such a way. Okay, so now if in a region like this there is a solution of the water wave problem, of the equation that I described earlier, because it involves harmonic functions and which are invariant under conformal mapping, the problem can be transformed into a problem in the half plane here, and ultimately everything can be expressed by an equation to be satisfied of this function w, which gives the parameterization of the boundary. So in the so the gravity wave involves just this blue term. The surface tension is here. So let's examine a little bit this term and see how they correspond to the Bernoulli condition in the original variable. So this is the Q, the Bernoulli constant that we assume to take this value. Then this is the vertical coordinate y, so gy, but y involved this scaling factor 1 over k. This corresponds to gradient psi squared. So the equation was 1/2 gradient psi squared equals 1/2 c squared minus gy, and then maybe plus surface tension or plus some undercurve. So in terms of w, gradient psi squared is this expression here. And here, if we look at the curvature, so if we think of a parameterized curve, then there is this formula for curvature involving the first and second derivatives of the functions involved in the parameterization. Yeah, so w is in the imaginary part, and this one in differentiate is 1 plus cw prime. So, and this power 3/2 in the denominator. So I guess this should be a familiar expression. Okay. So this is the curvature. And then for the hydroelastic wave problem, so same as here, but so we had the power 3 of the curvature, so which is written here with the coefficient 1/2. And there was this second derivative with respect to arc length, but now our curve is not parameterized by arc length, but by some other variable. So when we differentiate and using the chain rule, we get this additional weight. So it is this kind of rather messy expression. So I get, so these are the equations that I'd like to study, and that will give me solutions of the one-to-one problem. And we observe that w equals 0 is a solution for all values of c. So c is a parameter. Any questions? And so then we can forget about the fluid, and I will study these equations here. So the advantage. Their advantage is that they involve a function of one variable only, so this w, but they also involve the Hilbert transform, which it is non-local pseudo-differential integral operator, let's say. Okay. Yes, and now so we move, so I have derived the equation, now some abstract theory that will be applicable. So these are some very general results that are applicable in a lot of settings. So to some of you this will be very, very familiar, to other people maybe not so much. So bifurcation theory, at least in my the way I see it, involves the study of equations in Banach spaces that involve parameters. I'll give you examples on the next slide. So we want to determine the zero set of a function involving a real parameter and some element in a Banach space in a situation where zero is a solution for every value of the parameter. So it is customary to represent such solutions on a bifurcation diagram. So on the horizontal axis, we represent the real numbers where the parameter lambda belongs. On the vertical axis, we represent a Banach space where the unknown u belongs, although this is infinite dimensional space, so we make this toy picture of and by assumption, so we are interested in the zero set of a function, but which will not be defined everywhere in the space, but only in a certain region. And so when it is known that zero, so u equals 0 be represented on this axis, is a solution for every value of the parameter. So now local bifurcation theory.
Solution of what?
Sorry?
You have to write some equation.
Yeah. So it's f of lambda u equals 0. Okay. And so this is the most general. So we want to solve f of lambda u equals 0 when it is known that f of lambda 0 is 0, and the function is defined only in a region of the, so not maybe on the entire space. So now local bifurcation theory involves the study of solutions in a neighborhood of a point on the trivial line. So we want to know whether close to a point like this there exist some non-zero solutions, and maybe there is a curve of solution like we are going to see. While global bifurcation refers to solutions that could be everywhere in space, but which are connected somehow to the trivial line. So that would be, we don't quite know. So it is a very complicated structure of solutions, but they are linked to the trivial line. So bifurcation point, lambda 0 is this point here, which is a limit of non-trivial solutions. So there exists a sequence with, so this should be u instead of x, un instead of xn, and we have this convergence. And global bifurcation, as I said, so refers to solutions far away from the line, but which are still connected from the line. I will give you some example of Banach spaces and so on shortly. But this theory is based on differential calculus in Banach spaces and compactness. Okay, so differential calculus in Banach spaces is a generalization of the usual calculus in finite dimensional spaces, Rn. So we define what it means for a function between two such spaces to be a differentiable at a point. So the function is defined on an open set. We have a point. The function is differentiable if close to x0, it can be approximated by an affine function. So around x0, f of x0 plus a little something is equal to the value at the point plus a linear part acting on the increment plus some term which is sublinear, let's say little o. So that disappears in a limit. So you can think of like a Taylor expansion. These are higher order terms, but which are smaller than, so the differentiability captures the existence of a linear part of the function around x0, and Okay, also we can define partial derivatives for functions of two variables. So these are the just extensions of the familiar definitions from functions of several variables. So in finite dimension, such this linear operator would be represented by the Jacobian matrix of the mapping, which involves partial derivatives of all the components with respect to all the variables. But here in Banach spaces, we don't have any such representation. So it's just a linear operator. And for functions of two variables, you obtain partial derivative with respect to x if you keep the second component fixed and just allow the first to vary. So similar thing like in calculus, but now both x and so f has two arguments which are x and y, so we keep one fixed, and partial derivative is the linearization, let's say, with respect to the x variable, and in a similar way. Okay, so it is not so important to understand this in detail, but they do occur, they do play an important role in the description of the abstract results. So, natural way, it is possible to define higher order derivatives, a function of class Ck, and real analytic functions. Okay, so to give you a concrete example, so we take this problem of the Euler-Bernoulli rod. So it's not so important the meaning of these variables, what they mean, but let's say that the problem is described by a function of one variable, so phi double prime plus lambda psi phi equals 0, with some boundary conditions here, and lambda is a parameter. Now this phi, which is a function of one variable, we look at, well, what kind of function is this? So we see that two derivatives are involved. So it is natural for this phi to be an element of the space C2 of functions with two derivatives. And we put this boundary condition in the space. So these are my, this is the space X of all functions with two derivatives which are continuous, while if we allow the function f to act on lambda and phi in this way that appears in the equation, then this will be just a continuous function, and so the target space is the space of continuous functions. So this equation here can be regarded in this framework of bifurcation in Banach spaces. If x is the space C2, y is the space of continuous function. This is the formula for phi, and we want to solve f of lambda and phi equals 0. So this is the equation. So this is what happens quite often in theoretical PDEs. So equations are regarded as zeros of functions between Banach spaces, and this is, let's say, a simplest example. And so what are the norms? Here is different. So actually this is on y. Is this a primum norm in which convergence of functions means uniform convergence, and the norm on the other space on C2, so the x and y should be reversed, involves the function, the derivative, and the second derivative, so it's uniform, and convergence in this norm means convergence of the functions and the derivative. And now let us so calculate the partial derivatives of this function with respect to the two variables. So here there is a type again, so this is lambda. So we look at this expression, and first say we linearize with respect to phi at some lambda 0, phi 0, and using the above notation, this should be applied to some vector h. And so taking the second derivative is a linear operator, so it is like this, while sine, if you linearize around phi 0, is cosine time h. So this is just a way of making precise, let's say, the usual rules of linearization. And this should be, as I said, derivative with respect to lambda, and it should be just sine phi, but if we regard it as a linear operator, we have to, so it's multiplied by the real number which is applied. Okay, so yeah, this formalism is necessary for the results that I will present. Any questions or comments? Okay. So now definitions in some definitions in third year topology. So what it means for relatively compact set and compact set. So compact, if every sequence in that set has a convergent subsequence. So while for real numbers and finite dimensional spaces, bounded sets are relatively compact, in infinite dimension this is not true, and that's why we need to make these assumptions. While a compact operator, it is one which maps bounded sets of the domain into a relatively compact subset of the domain. And compactness will be used in my problem in this very basic way. And not exactly this, but this is the main idea. So if we have a set which is bounded, like a family of function which is bounded in C1, so it means that we have a bound on the function and a bound on the derivatives as well. And this is relatively compact in the space of continuous functions. So it has a subsequence which converges uniformly. Okay, and so maybe we could take a break now. So, and what I want to do next, so I would like to return to these equations, which I consider of the form f of c and w is 0. So the w, it is the wave elevation, like in that parameterization at the top. So c is a real parameter. And as I wrote on the bottom, so we do have that f of c0 equals 0. Now I'm interested in solutions with w different from 0. So this is why this setting of this general setting of bifurcation problems is applicable to this equation. Yes, so let us maybe take a break and some coffee, and I'll continue with the abstract results and what they give when applied to these equations.
Okay, maybe one question.
Yeah.
In the elasticity,
Yes.
the first term is localized bending, yes? On the right hand side.
Both of them occur like this.
Bending, and the second is stretching.
No stretch.
No stretch.
No stretch?
It's still k double dash plus half k.
But where does this come from? Is there
Where does it come from? We should add this.
No, I could combine them both. I prefer to keep them separately. So you can put both a multiple of curvature and this. So maybe you think that
Which is very more functional, yeah?
Yeah. This comes from the exactly, yes.
Okay.
Okay, so let's have a 10 minutes coffee break.
Coffee break.
Can go for the coffee on the other
Yeah.
building.
And where is the coffee?
Can go on the other building to take the coffee. Okay.
Yeah.
We didn't prepare the coffee for that. I'm not sure how you got it from that because of the other thing. Yeah. What is the thing? recording. so when you look at the recording, will be a half an hour break.
Or still recording, right?
Okay, so I'll go a bit more quickly over the abstract theory. So this mention the statements of four results. So, as I said, there are two main ingredients in bifurcation theory: the differential calculus, the study of linearization, and compactness. So, the first result is about local bifurcation. Gives you the existence of a curve of non-trivial solution in a small neighborhood of a point on this axis. This is Crandall Rabinowitz. So let us look at first at the conclusion. So okay, same hypothesis. We have function between Banach spaces on an open set. We have a line of trivial solutions. So we look first at the conclusion. So there exists a curve parameterized by S. So lambda is a function of S, U is a function of S, which for the value 0 of the parameter, so it intersects the real axis. We have some information about the tangent to this curve, and this is saying that the solution set in a neighborhood of this point on the axis, and so the set of non-trivial solutions is exactly consists of this curve here. So the full solution set is the line segment and this curve, and this is the conclusion. And to reach it, so the assumption are so we are looking at a particular point on this line. So if at that point the kernel of the linearization has dimension 1, the range of the linearization for dimension 1, and we also have a transversality condition involving a second derivative, but all of this fine. So you just essentially need to calculate some derivatives of the functions at this point. And if these conditions are satisfied, then you get a local curve. Yeah, so this is not surprising. This you can check in all of these problems, and it works. Okay, so more interesting and important is how this curve here continue in space, whether they continue to solutions of large amplitude. And here somehow the idea is that we want some results that show that the curves do not just stop somewhere, but they can be continued either until they go to infinity, or until you approach the boundary of your domain, or you return to the same point, or you return to some other point on trivial line. So these are the type of results that are obtained as conclusions. So first theorem of Rabinowitz, so the same assumption for the as always, and we assume that we have a local bifurcation by Crandall Rabinowitz, although this can be relaxed to so we can replace this by some more general conclusion. But the really important assumption in this for this theorem to work is that the function involved in the equation so is the identity minus some compact operator, well, unbounded closed sets. But these functions are called the compact perturbations of the identity. So your the expression that occurs in the equation, you have to be able to put it in the form identity minus or plus a compact operator. And then the conclusion is that under this assumption, so where this is crucial, I emphasize once again, we look at the connected set of solutions that contains the local, this local curve ensured by Crandall Rabinowitz. And the conclusion is that at least one of two things happen. So either this, so all solutions that are connected somehow to this curve, so this is what we are talking about. So either this family of solutions reaches the trivial line at some other point, or it goes, so is not contained in any bounded closed set of the domain. So no matter how you choose a bounded closed set, this solution goes out. And this, because every open set can be written as a countable union of such bounded closed sets, and this is saying that this family of solution goes out of all of this. Now there are two possibilities: either it goes to infinity in the case of unbounded, or it approaches the boundary. So we have, there exist solutions either of arbitrarily large norm or of arbitrarily close to the boundary of the domain where the function is defined. So return to the trivial line, or going to infinity, or going to the boundary, key assumption, compact perturbation of A. Okay, we have something that I can, that is a more refined version of this theorem of Kielhofer, so the conclusions are the same. Here you don't need to write your operator as a compact perturbation of the identity, but again, you need to have, so you have some more complicated assumptions to check, that inverse images of bounded closed sets are compact, and the linearization, and there is a condition about the spectrum and eigenvalues and so on. So this is quite a bit more complicated and require more work to be verified. I'm actually not going to use it much. And the final result is the real-analytic theory that goes back to Dancer and has been put in a more precise form by Buffoni and Toland. So again, we want to study the same problem, but under the key assumption that the function is real-analytic, so which means that it's differentiable of any order and can be written as the sum of its Taylor series properly defined. So this involves some technicalities, but in all the one that we've found, we do have this real analyticity. I should have said that the previous theory is based on topological degree. So here let me go first to the conclusion, and then we'll discuss the assumptions. So the conclusion is that this local curve can be continued as a curve, and this curve satisfies either of two properties. So either it returns, it is a closed loop, it returns to the point where it has started from, so it is a closed loop, or again it eventually leaves, quits every bounded closed set of the domain, which again as before, so it means that either goes to infinity or approaches the boundary of the domain. But this is a curve, so while in the previous theorem we did not know, I mean this was just a connected set, so which would have been much more complicated than a curve. And as for the assumptions, again, so it is, we need some compactness assumption again, so the solutions that are in a bounded closed set of the domain are actually in a compact set. And again, something about the linearization, but this is not so difficult to check. Fronthold of infinity 0. I'm not going to go into these details. So the conclusion that that these theorems are giving us again is just we don't have just a very small local curve, but this curve can be continued somehow either until, well, it may return to the same point that it started from. It may end up at another point on the trivial line. It may go to infinity, or it may approach somehow the boundary of the domain. So yeah, but so this is these are the results. So they are all very general. And well, in a way, you could say that maybe the information they offer is somewhat limited. But for example, if we knew that the solution branch goes to infinity, so this means something is large for your solutions, either the amplitude or the parameter or whatever. And it is, of course, of interest maybe to rule out the second possibility, if possible, and to be more precise in what happens with the curve of this curve of solutions. So how? But once again, the assumptions of this result involve always some compactness. Yes, so just to show how this applies to other waves. So local bifurcation for gravity waves. So the equation is like this. It involves this W, the wave elevation. Always in the equation we have this this parameter that I'm going to denote by lambda, and the function that we want to make it 0 is here. So what are the right spaces? So we have derivatives. So C1 and alpha, and so the alpha is a Hölder exponent. So because Hilbert transform maps Hilbert functions into themselves, Hölder functions into themselves, but Hilbert transform of a continuous function is not necessarily continuous. So this way it's necessary to work with Hölder functions. This 2 pi means periodicity, this little e means even. So we look for symmetric solutions. These are the natural spaces. We linearize the function at 0. So you see this is a cubic equation. So we expand all of this, and we keep the linear terms only as this kind of expression. And if W has an expansion into cosine, then this is the how the linearization acts on the function. And we get, so in the Crandall Rabinowitz, we have to study the kernel, the image, and the transversality. So, but okay, so let's say the kernel is the key point. Bifurcation takes place exactly at the natural number, and for so there is a sequence of bifurcating curves, and we get lambda equal 1, c equals c squared equal gk. So in the finite depth, this would give the dispersion relation. So this does not lead to. So it's a rigorous way. I mean, it shows that the nonlinear problem has solutions of a small amplitude, and we determine at each one point on the line they bifurcate. So this gives a relation between the wave speed and the wave period. Okay, so. On the other hand, for these 2 other problems, generically the kernel is again one-dimensional, but there are some exceptional situations where it is 2-dimensional. So this is the situation that is known as Wilton ripples. That I'm not going to get in the detail, but the structure of the solution set close to the trivial line can still be studied in full detail, but in a much more complicated way. So this is about local bifurcation. But I want to discuss more global bifurcation. So the gravity wave, so neither of the global theorem is applicable, because with the form that the equation was there, it is impossible to prove the compactness requirements. However, the global bifurcation can be proved provided we transform the equation to an equivalent form, which is originally due to Babenko. So I'm not sure if you might have heard of this before. So again involves the Hilbert transform, same functions before, same parameter. So this is not just an algebraic rearrangement of what we had earlier, but so you can prove that something like this is equivalent to what we had earlier. So this is cubic W and then square. And this is just quadratic. But we try to. So the idea is to try to arrange this equation in a form of a compact perturbation of the identity. And the key point for doing this is that it can be further rearranged by algebra in this way, so that we exhibit this difference, which is called a commutator. So it involves Hilbert transform double and double prime, but in a bit different shape. So the basic idea of what we are trying to do is to exhibit the most singular terms and to invert them. And in the original form, so the most singular are this and this and this, so which involves the loss of a derivative. And by this transformation, it doesn't seem like we have achieved much, but the nice thing is that this commutator is actually smoother than we might think at first sight. So for W with one derivatives, so both of these are in Y with zero derivative, but the difference of the two actually is in C1 delta instead of C0 alpha. So because of so this is quite subtle, so subtle cancellation, this term is more regular than, the difference is more regular than the individual terms. And so this is, so if we look here at the most singular term, so now it remains only this one. So we divide the equation by this quantity, which is smooth, and we invert CW prime, and what remains in the right hand side as a consequence of this commutator estimate is a compact operator. So we have the equation is in the form identity equal compact, and exactly because of this smoothing effect that we have exhibited. So as I mentioned earlier, when I discussed compactness, bounded sets in spaces of functions with higher regularity are compact in, so bounded set in C1 is compact in C0. So exactly this higher smoothness implies compactness in the space that we are working in. That's roughly the idea. But it was really essential to use this form of Babenko and to write it in this form. So, and this analysis doesn't work for the equation in the form that we originally exhibited. Okay, and for the gravity wave problem, so it can be proved, it has been proved that the solution curve does not return to another point on the trivial line, and also it doesn't return to itself because of so-called the preservation of nodal pattern. So solutions on this curve correspond to waves that are remote, while solutions on these other bifurcating branches have a different shape with more oscillations. And it is quite tricky to prove that this monotonicity is preserved all along the branch. But so it is this fact that prevents it from returning to another point or returning it to itself. And then we look on the boundary of the domain on which the operator was defined. So it was 1 minus 2 lambda and so on. So if we interpret it in the physical plane, so the boundary of the domain, so a point here, if it corresponds to a wave at all, so this means that this is 0, so this is 0. So this will be a wave with a stagnation point, which occurs at the crest. So the fact that the solution curve would approach the boundary of the domain in which the functions are defined means somehow that the solution would approach these extreme waves. So it is not easy to prove that actually there are solutions exactly on the boundary of the domain. So the bifurcation theory only says that there are solutions that approach the boundary somehow, but there are, yeah, so it is non-trivial to prove that there are solutions of the boundary, so which are these extreme waves of Stokes, but yeah, so their existence is, I mean, is built on the global bifurcation theory that I explained so far. So these extreme waves are indeed limits of solutions of large amplitude that lie on a curve starting from a trivial wave and going to the extreme one. Okay, so what I said at the beginning, that this picture of what kind of solution does the gravity wave provide that Stokes believed that there is finite parameterized amplitude. So this is proved as a consequence of the results that I described. Okay, and now briefly about these two other problems. So in the gravity wave, so compactness was a consequence of the commutator estimate in the Babenko formulation, so which was trickier. So now, even though this looks more, these two problems look more complicated, compactness is actually easier and can be proved more directly. So again, I rearrange it somehow to exhibit in the left-hand side the most singular term. So here, which is the curvature, which involves second derivatives. Here we have only first derivatives. And in the other formulations, so I am splitting the two terms due to hydroelasticity. So the one involving second derivative with respect to arc length, I move it, I put it on the left-hand side, and the other I put it on the right-hand side. And we look again at the most singular term. So these gravity terms and so involve one derivative. These terms involve second derivatives of W. These second and third and fourth. Yes. So in the end, the highest order of differentiation is 4 for this equation and 2 for the capillary-gravity wave problem. Okay, and now one has to try to write again these equations in the form of a compact perturbation of the identity. So we try to invert the most singular term so that we have the function is equal to something which is smoother, so which is a compact operator. But the highest derivatives here occur in this combination. However, there is and there are two of them, and the analysis does not go entirely directly, but there is a little trick based on complex analysis that enables us to separate just the second derivative of W out of this and get rid of this other. Namely in the following way. So we multiply this the first equation by the power 1/2, so that in the denominator we just get this expression. So with exponent 1 instead of 3/2 is just 1. And the remaining thing, quite complicated as it is, I will call it f. Okay, and now we have this lemma in complex analysis that, okay, so here f depends non-linearly on w, so it is this expression multiplied by something. So we ignore that. So we have this lemma in complex analysis that two functions w and f satisfy the relation on the preceding slide, so this kind of thing, if and only if w prime can be expressed in terms of w prime Hilbert transform f and the Hilbert transform of f in this form. Okay, so yeah, I will not go into the details. It is elementary, but involves some complex analysis. Okay, so going back again, so we have this expression involving second derivatives of w, but both here, and f involves only first derivatives because of this and this, so only first derivatives. But then rather than this combination of two expressions involving second derivatives, if I write it like this, the expression in the right hand side involves one derivative of w and Hilbert transform and so on. So I have managed to isolate the second derivative to occur only once on w in here. So this means that this term is smoother than this, but this involves taking two derivatives, while this involves taking only one, and then the second derivative can be inverted by integrating twice, and then we have w equals something which is smoother. So it is a little trick that transforms the equation in such a way as a fixed point of a compact operator. And this is an essential ingredient in applying the global bifurcation theorems, which would not have been applicable directly. I mean, so you just look at this, you cannot verify the assumptions. But if you do these little tricks and rearrangement, you put it in a form where the theory is applicable. Okay, so now for the second equation, first of all, I would like to isolate the curvature somehow like it was before. And for this, I need to do the following step. So I multiply by xi, by zeta, sorry. And then I integrate, then I multiply by xi, and then I integrate. So basically, I invert these two equations that appear here. And then I am left with an equation which, on the left-hand side, so there is a term like before, on the right-hand side, something much more complicated, I mean, a real mess, but in which, if we count the number of derivatives, so this involves taking two derivatives. This also involves taking two derivatives, but as I said, we integrate twice to get rid of these derivatives here. So in the end, the left-hand side involves is differentiated a higher number of times than the right-hand side. And then I do I am applying the so multiply, integrate, do the same trick as I did before, multiply by this, use again the lemma, which leads to a really messy expression, but the point is that I write the equation w equals a compact operator of w. Okay? And so this means that for these two equations, global bifurcation theorem are also applicable. Yes.
And what do you mean? the infinite branch of solution or not?
I will get to this. And then, okay, so these are the relevant function spaces. The open set is must include this condition because this expression occurs in the denominator. And the boundary of the solution set so contains those points for which this is zero. So the parametrization is singular. So unfortunately,
No. The question is, there is no some kind of monotonicity, like
no.
gravity
Well,
waves.
I wrote it here.
Therefore, the closed.
It is possible, yes.
Therefore, it may be very small solution finally.
This I agree, yes. I had this in mind to mention that this is a big problem. I mean, if this is closed, it would be very small actually, and so we haven't.
We don't know the solution.
Not yet. But this appears well. But on the other hand, the topological theory says that the continuum of solutions will go and reach some other point. So I know, so this is another possibility. And so this means that it does something non-trivial, but maybe I could still move very close to the trivial line. So this is again not very good. So it is not clear that...
Therefore, it is not come to singularity. It may be from smooth to smooth. And
yes. But I think that even in the capillary-gravity waves, some numerical computations show that this happens. So maybe have you observed this? Like a branch connecting two bifurcation points. So it is non-trivial, but then it returns to the trivial line again. So I'm not exactly sure, but this is my impression that this is really a possibility. So yeah, so we don't really know that these solutions constructed are in any way of large amplitude. Okay, but still, I wrote the equation as identity for compact, so which is more than the local theory tells us that then there is only a small branch. So this is so the theory is much more complete in the gravity case, where the solution do reach this kind of solution with singularities, and for the other two problems.
What is the singularities in capillary-gravity?
Well, here to my mind, just
capillary-gravity. But
You can have 180
in
degrees.
two-dimensional case for hydroelastic waves, it seems there is no singularity. In three-dimensional case,
no, but yeah. So this is an interesting question. So what happens to this branch of solutions? Yeah, so you try to continue as far along as you can.
We stop the computation when 2 points touch.
no, this is a difficult question because we do only this function W of phi of S of something like this, yes?
Yeah, I mean,
Therefore, self-intersection is, in principle, which is possible.
that's right. We always find a self-intersection solution. And
But the problem, if you solve this intersection, it's not singularity or something like this.
No,
Yeah,
it's not
in the-
singular.
Everything is okay,
it
but
is
it's
not.
simply like this. You need some monotonicity argument shows that it is graph of something.
And I computed the solitary wave for capillary gravity waves, depression wave. I can down to c equals 0. The propagation speed equals 0.
Yeah.
And that happens also in the flexible gravity waves. You can have some steady structure, c equals 0.
Non-trivial,
Non-trivial.
but it is one-dimensional.
One dimension.
Under pressure.
Yeah.
Yeah, that's.
I would be happy
If
if
you
one.
have the bubble, so
Yeah, the bubble can
change the
that's
shape.
right, that's right.
That's something
The steady state.
I would be happy even with a proof of existence of a self-intersecting solution, because that would mean that it is far from trivial, and so the existence of such large solutions is not known by other methods as far as I know. So. And we do have these explicit examples of pure capillary with Crandall's waves that become overhanging and then self-intersect and so on. And so I think we expect the same to happen in the for both of these, I believe, right? And capillary-gravity and the hydroelastic and. I think there have been some computations that in the hydroelastic wave problem also on the branches there are solutions with self-intersections and some monotonicities. I'm not sure whether, but the usual arguments do not apply. I mean. How preservation of monotonicity holds in the gravity case, the method does not seem to work for these more general problems because of higher derivatives involved. And okay, so yeah, this is what I have to say. So well, just very briefly. So all of this has heavily used complex analysis and Hilbert transforms, which does not work with vorticity. With vorticity, existence is studied in a different way using this partial hodograph transformation that we interchange the roles of y and psi. So instead of seeking psi as a function of x and y, we seek y as a function of x and psi. And these two coordinates describe half plane, but then the equation is much messier, so even though it comes just from the Laplace equation by inverting the variable. But the theory has been run for this kind of problem as well, and it involves Kielhofer theorem that I also have on the slides, but did not get to speak about in any detail. Okay, so yeah, so global bifurcation does have something to say about the existence of solutions of large amplitude for wide variety of problems, so not necessarily restricted to wonder waves. It is a classical theory that is well known by some people, on the other, not even among, yeah, it's maybe not very well known even among the analysts, and so somehow in this talk I wanted to give a flavor of the theory for people with more applied background, but unfortunately we did not have many of them here. So thank you.
Okay, I think it's very good talk, yeah?
Yeah.
So yeah, if you have more questions, we just can go back to the coffee and
Yeah,
discuss
okay.
Okay. One question. You never use variational properties.
Not here. I mean, it's. You mean a combination with bifurcation or separately? Yeah, so there is different approach based on.
For variational problems, the bifurcation theory is much better.
In what sense? This I actually don't know.
Oh, for example, okay. For example, I give the following example. You need some. What's the degree of mapping? Some calculate some quantity in Crandall Rabinowitz theorem. Yes.
Yeah.
If the problem is variational, we use the second quadratic form and signature of this
Mm.
Therefore, maybe the degree, the topological degree may be 0, but signature are different.
Yeah.
In this case, you have bifurcation in the reaction case.
Okay, yeah, this I agree, but for the local theory, I think more complete analysis has to be done by Lyapunov, Schmidt, and with this
It is
Wilton,
very-
Ripples, and yeah,
it
and
is-
bifurcation could help indeed.
It is very complicated stuff. Okay.
I have a question. So,
Yeah, yeah.
so does your work, does your method work for solitude?
Not as directly, so no, you.
Because,
a bit of it can be, part of it can be adapted, but it is much more complicated.
The reason I asked you this question is for fractional gravity waves. Solitary wave doesn't bifurcate from 0 amplitude.
Say it again, for what?
Yes.
For fractional gravity waves, solitary